on t-intervals. What is a t-interval? Why do we care about them? What is a t-interval? What does t mean? What is it? I know it's been 5 days. I'm a bastard for asking this question first off. I've got an in-class quiz to practice this. Ben, help me. Or anybody help me. I heard it. Working on it. Okay. T-interval. Versus what? Let me ask you that. Versus what? Okay, good. Versus a z-score-based interval. Good, good. How is a z-score-based distribution and a t-score-based distribution? How are they similar? Do you remember?
They're the same general shape.
Love Elizabeth. Same general shape. They're both bell curves, yes? They're both bell curves. So that's how they're similar. How are they different? Do you remember?
One is for proportions, the others for averages.
Good. Pedagogically, that's what I want you to think of. When you're dealing with proportions, you want to use a bell curve, the z curve. And when you're dealing with averages, you want to use the t curve. That's the pedagogical takeaway. I love that. Thank you. That is the pedagogical takeaway. And it really, honestly, it makes your life easy because, and this is the PowerPoint that's already sitting waiting for you guys from last week. I'll link it again today, obviously, into today's cell on the schedule page. Okay. The trick is n's a sample size. As it gets large, I put large in quotes because everybody seems to have a different definition of large. But as your sample sizes get bigger and bigger and bigger, z and t collapse on each other, as you might remember from last week. Okay, they look the same past the point. But when n is small, very small sample size, which was the whole point of Gossett creating this distribution, they're vastly different. Do you remember how they're different? How the t distribution was different when the sample sizes are small. Do you remember? You can draw the arrow for me.
Wider.
Good!
Shorter and wider.
Brandon, it was shorter and wider. Good, good, good. I call those fat tails. Okay? They got fat tails. We got more real estate in the tails. And the reason, it drops the middle, but all that area was there has to go somewhere. But since it was symmetric, because it's a bell curve and symmetric, the area then shoots off into the tails, making the tails rise up. And that's why, again, you have to go further out with the t-scores to pick up the same level of confidence. Where it only takes 1.96 on a z, it might take 2.2 or 2.3 or 2.4 on a t. Now that difference becomes a little bit less meaningful as the sample sizes get larger because they start pulling in. I have a little chart we can refer to back. But the idea is you pick up that extra confidence with the fatter tails. Fat tails. Make sense? You don't have to memorize this. I'm just trying to revisit the idea so you remember what we were doing last week. Okay? And here's the fat tail idea. Okay? So these are the critical values you need to get 95% confidence based on a certain number of sample sizes. So when you have a sample size of 10, you got to go out to 2.262 to 3 decimal places of precision to get 95%. If you increase your sample size to 15, 2.145 does the trick. 20, 30, 50, and so forth and so on. And that's large. I don't know what else to call it. Whole lots. 1.96. 1.96, you remember, that's the z-score for 95% confidence. But the thing is, it depends on how precise you need to be. If you're talking about drug dosages for a medication, I'm going to use as much of this as I possibly can get. All right, we're going to do a little experiment in class today. We might not need that much precision, but just realizing that these are collapsing down. And just one quick little refresher, you might see this term pop up in your stat class, especially those of you taking later stat classes. Coincidentally enough, I got an email two days ago from a former stat student who then saw this term and thanked me for bringing it up every once in a blue moon, because now he understands it. Degrees of freedom is always defined to be one less than the sample size. It does have a meaning, and in later stat classes it might become more important to you depending on what stat classes you take. And it is, not right now though. But just so you hear the term and you see it. So when you have a sample size of 10, you've got 9 degrees of freedom. Sample size of 15, 14, 20, 19. I used to make this part of the class. Students don't like it very much, totally fine. And it's not crucial for 244. It's good that you see that term a few times as we go through it. And you'll keep seeing it as we go through the course. But I'm not going to test you on it. But if you see it later on, like the student Andy sent me the email, he's like, thank you. Thank you because it makes sense now. And thank you for the binomial. Thank you for the chicken experiment. It's like, it all makes sense. It's all chickens. I'm like, oh, yes, it is. It is all chickens. Because it is. Anyway, I won't get sidetracked into that. So, sample size n, degrees of freedom n minus 1. Just keep that in the back of your mind somewhere. You've seen it before in the sample size calculation with the n minus 1 in the denominator. That's why it was there. So we'll get back to that too. All right, shut that down for the time being. what I want to do today is I want to put this to work one more time. I want to